Hi friends, in today's tutorial we'll talk about discretionary signals backtesting using VectorBT Pro. For this project I extracted the Telegram signals from this free Telegram channel called Green Pips, which is loaded using vbt.csvdata.fetch module in the signals data variable. So for the purposes of easy backtesting, we will focus on one instrument, namely XAU USD, which is fetched into this data variable. A date parser function is used to parse the timestamps in Unix epoch format at UTC0 time zone into this date time format in milliseconds. So in this cell, we are just cleaning up this order type column in the extracted signals to remove trailing white spaces using rstrip, and then doing a quick check to see if there are any invalid signals with 0 or null entry prices. It seems the signal extraction went well and we don't have any invalid signals. We also see that the order type column is having unique order types like sell, buy stop and sell stop. For those who are unfamiliar, buy stop and sell stop are two types of pending orders. So in buy stop, the order is executed at a price which is above the current market price, and the analogy is similar to catching a flying rocket, meaning the price, and expecting that the price will still go higher, and you will set a stop loss that is below the current market price. The converse is true for a sell stop, where you set the order entry price below the current market price, and it is similar to catching a falling knife, expecting it to continue to go down further. If you had been tinkering with VectorBT a lot, you would have noticed that we use named tuples quite often. A named tuple is an extension of a regular Python tuple and supports custom data types that enrich built-in tuples with extra utilities. So they are very useful in contexts where we need to create a data structure that can be accessed by both the positional index and the named attribute of the elements. So first we are creating this order type T named tuple, which has the name order type T, and then 4 fields representing the 4 unique order types in our signals data, namely the buy, sell, buy stop and sell stop, which you can see by using this underscore fields and underscore name underscore in this print statement. Next we create this transform signals data function to map the order type columns having string values to integer values using this order type named tuple for use in our number functions further down the line. So we don't need two columns in this signals data frame. Data frame. First is this message column, which contains the raw telegram messages from the signals data, and since we are focusing on only one symbol XAU USD, we pass it as a default argument to this transform signal data function, and after that we can even discard that symbol column and just select the remaining columns. So from this data frame output we see that there are about 232 signals for XAU USD, and the order type column has now successfully been mapped to a numerical data type. We also create two other named tuples which will act as containers to store various arrays. First is the signals info named tuple, which contains the fields like timestamp to store 1D array of timestamp values in integer format. The order type field stores 1D array of order type values, which we just saw how to remap from string to int data type. The entry price field stores 1D array of entry prices in float data type. The SL field is to store a 2D array of stop losses in float data type, and the TP is to store 2D array of take profit levels in float data type. Now in these 2D arrays like SL and TP, the column shape of the array represents different levels For example, in TP field, we have 4 TPs, TP1 to TP4, indicating 4 different TP levels. But for SL, we only have one stop loss per signal in this data set. So the next named tuple we create is this temp info named tuple, which contains only integer data type fields like TS bar, which is to store a 1D array of timestamp values in nanoseconds of the integer data type. So the purpose of TS underscore bar is to mark the bar, that is the absolute index of the row, where we saw the signal for the first time. We could have also created a Boolean array with true for signal seen, but for more consistency, we use this named tuple format for storing rich information. Basically, you can think of it as a 1D array where each element corresponds to a column or a signal. Before the signal is hit, the value is -1. After that, it becomes the row index, and from that point on, it never changes. Having this array is important because we want to skip our logic if there is no signal yet. The entry price bar field is to store a 1D array of row indices where each entry price was hit, and that again is in integer format. SL bar is to store a 2D array of row indices where each SL level was hit. This field has the same shape as signal info.sl, and likewise TP underscore bar is to store a 2D array of row indices where each TP level was hit. This field again has the same info shape as signal info.tp. So we have our market price data and our signals data. Now we need a function that executes the various orders from the signals data, right? So this is what we will see now. This order func nb function will deal with the execution of various entry and exit orders, along with position management for the purpose of backtesting our telegram signals. The main characteristics or concepts of this order func nb are representing each signal as a separate column with its own starting capital. We need to keep this point in mind for the rest of this tutorial, that is, signals are represented as columns. The order function is executed at each bar and column. If the current bar contains a signal, we will execute the signal logic. Order functions can issue only one order at a bar. Thus, if multiple stops were hit, we will aggregate them. We will go all in and then gradually reduce the position based on the number of stops. Sometimes we may see two signals occurring right next to each other with different stop losses. So in order to maintain consistency in the number of rows, that is levels, all these stops are stored in a single array. That is, all stops across all signals must have the same number of rows or ladder steps or levels. Thus, we need to pad the columns where there are less stops with NaN. So you could have also run this simulation on each signal separately, which would be quite slow, but in such a case you wouldn't need padding. Finally, we will run this order function, order func nb, using this portfolio dot from order function at the end. We will come to it when we run that simulation here. Going back. So first we will go through a couple of helper functions which are used in this order func nb function. The first is this hash data nb function, which checks if the open, high, low or close columns are not NaN using this core VBT function called selectNB, which you can access by clicking the go to definition in VS Code. And as you can see in this selectNB function, we pass a named tuple as a context object and also an array, a two-dimensional array. The next helper function is actually a wrapper function for an existing VBT function called checkPriceHitNB, for which we again pass as arguments a context object, the price, and two Boolean arguments called hitBelow and CanUseOHLC. HitBelow checks if price hit against the low or checks if price hit against the high, and the other Boolean argument CanUseOHLC which is when false, will check only against the close price. So this check price hit NB returns the order price where the order was filled and a boolean output called hit. The order price isn't necessarily the price that has been hit. If the price was hit before the open, for example, the order price is set to the open price. Now moving on to this main order func NB function. So the first argument again is the context object, followed by our two named tuple containers, signal info and temp info, which we just created earlier here. Signal info and temp info. The context is basically our OHLC data, and first we check if it has any valid data using this hash data NB function, our helper function, and if the bar contains no data, we basically skip it by returning this order nothing object. Assuming we have valid bar data, we store the column data corresponding to a signal and the row corresponding to a bar. So c.I means the row index number, c.index means the time series index, the timestamp, and c.call means the signal. So we define these various flags representing various buy and sell order types just for pure convenience. You may notice that we only have buy is equal to buy market or buy stop because selling means not buying. So we only need to check whether it's a buy operation, and if not, it's automatically a sell operation. That is, sell is equal to not buying. That's the logic. So here we can use OHLC or boolean variable to true, set it to true to indicate that we can use any price of the bar, that is open, high, low and close, to check for the entry. Thus if temp info .ts underscore bar signal checks if a signal has been discovered in this line checks if the signal has been discovered in the current bar. So if it is -1, it means it hasn't been discovered yet. So if a signal was discovered, so we store the current row index in a temporary array such that later we know that we already discovered this signal. The signal has a granularity of seconds, which means it belongs somewhere in our bar. So we need to notify the functions below that they cannot use the full OHLC information and only close. So we reset this can use OHLC back to false. So this is to avoid using prices that technically happened before the signal. Now we see that the entry order hasn't been executed again. If it is not executed, we execute the entry order, which can be a buy market or a sell market. The execution depends on this order type, right? So first we check if it's a buy market order. If it is a buy market order, then we store the current row index in a temporary array such that future orders know that the order has been executed. The order is executed using this VBT PF order NB function, where the two np.numpy.infinities represent the size and price of the order respectively. So like we do for the buy market, we also do the same for the sell market condition, market sell. Except we use a negative minus np.inf in this VBT PF order NB function to represent the sell order. So by default, when the sizer is amount, then positive size plus sign means buy and negative sign means sell. So let's move on to the execution of pending orders, that is buy stop and sell stop pending orders. So a buy stop order is entered at a stop price above the current market price. Since it's a pending order, we first need to check whether the entry price was hit, for which we first use our check price hit NB function which returns the order price and the Boolean hit. If the Boolean hit is true, we execute the order. So the same steps are used for the cell stop, except we pass this minus np.inf for the size in this VBT PFNB order NB function to indicate that it is a cell type order that is to be executed at the order price. Next, we will talk about stop orders or exit orders, which can generally be of two types. As you would know, a position can be stopped out if the price hits the stop loss that you have given or the take profit that you have set. So before checking for a stop loss, we first need to check whether the entry order was executed, and after that we are still in the position or whether the position was closed out already in this c dot last position signal not equal to 0. So I will illustrate the for loops and this section of the code with a working example. But before that, before we do that, I just want to highlight a few common things. So as you can see, the structure of the code for checking take profit or stop loss hits is the same. It starts with this NSL levels, and then there is this for loop, and inside that some if conditions. Likewise, instead of NSL levels, we have NTP levels, and so on. So we start with checking for stop losses, because as you know, chronologically the stop loss would come before a take profit. So generally the telegram signals contain only one stop loss per signal, but in order to make this pipeline more flexible, SL ladders have been allowed even if we have none in this data. So next we will see this take profit ladder system working with a working example using some sample data. So this is the first case study. So for this first case study, let's assume we have 3 TP levels here. So this code segment derives the number of TP levels that are defined in this signal and the number of levels that have already been hit. So from this output, we see initially none of the TP levels have been hit. So now we are creating this loop that iterates over the TP stop prices in reversed order. The order price, the order is reversed because if the last stop price has been hit, all the stop prices defined before it are automatically getting hit too. So we only need to iterate over those prices that haven't been hit yet. So let's assume that the first take profit stop price has been hit with this k is equal to 0. So the size here represents a target percentage size. That is, we want the column value after the order to be 66.6% of the value that is right now, which means we are basically removing 1/3 of the position value when the first take profit stop price is hit. So let's look at what happens if our second take profit stop price is hit instead. So here we see that 2/3 of our position value is removed at take profit 2. So finally, when the last take profit is hit here, the position is now fully closed. In summary, we removed an equal chunk of the position value, that is roughly 33%, at each take profit level using the above logic, like TP1, TP2, TP3. So moving on to the next case study, where we have a take profit ladder with only 2 TP levels, but there are 3 rows because some other column is using 3 levels of take profits. So in such a case, this array is padded with np.nan. So we see that the code has correctly determined the number of take profit levels in this ladder, which is only 2, excluding the nan. And so since we only have 2 TP levels in our TP ladder, so when the first TP level is hit, we remove 50% of the position as opposed to like 33% we did in the previous case study. And then when the second or the last TP is hit, the position is fully closed. Next, we will see about matching timestamps from our signals data to the price data. So the timestamps are stored as the index values in our signal underscore data variable, which we read type converted as integer. So since our telegram signals are of the second granularity, which means the message can come at any second of any arbitrary minute, while the price data is of the minute granularity, we need to round the timestamp of the telegram signal data to the nearest minute. So timestamps represent the opening time, right? So thus if we have like 59 second and 19, 29, 28, 59, this still belongs to the minute 1928, even though we are 59 seconds elapsed in that minute. So each value in our timestamp is represented in nanosecond format, which is time elapsed in Unix epoch, which starts from 1st January of 1970. Since they are just regular integers, we can do operations such as modulo, which will remove the remainder from dividing the timestamp by a minute to effectively discard any seconds, milliseconds, microseconds, or nanoseconds from the minute we are currently in. So here we are using this VBT DT underscore NB M underscore NS to convert it into the total number of nanoseconds in 1 minute by doing this modulo operation. Next, we will run the actual simulation with our signals and the market price data. First, we will load the necessary array values such as timestamp, order type, entry, SL, and multiple take profit prices in the signal info named tuple container that we created earlier. So these are the arrays. We put these arrays in the signal info named tuple. So remember that this temp info named tuple container we created earlier to store the bar data for timestamp, entry, stop loss, and TP, right? It turns out that we need to clear this temp info container at the start of every simulation. This is because temporary information gets overwritten during the simulation because it acts as a memory where signal functions from the future access information written by the signal functions from the past. So since we don't want to use like dirty arrays, we have to rerun this build temp info function every time for each simulation so that the temp info named tuple container is cleared for subsequent simulations. So now we run the actual simulations. Of course, here you can print the shape or the number of SL and TP levels that we are actually using in our simulation. So altogether we have about 6 orders. First one is the entry order, and then 1 SL order, and then 4 TP orders. Now we run the actual simulation of our signals data using this vbt.portfolio from order function, where we pass this order func nb function that we coded earlier. And you might wonder what this tile is doing in this broadcast quarks argument for, right? Since we don't broadcast data against any other array, VectorBT doesn't know anything about our signals array and will simulate only one column that is in our data. For example, if our data has say 500,1 shape, then the simulation will only run on one column. Thus, we need to tell it to expand the number of columns to the number of signals, which is as simple as providing this tile argument to the broadcaster. So under the hood, it will replace our example shape of 500,1 with 500,232, which is the number of signals we have. Also note that you can pass an index instead of a number. For example, you can pass a signal info dot timestamp or the Telegram message ID as pd.index. So they become the column names in the new portfolio. So we can print the orders executed in the simulation using this pf.orders.recordsReadable, and we get this output. Now you may be wondering how this size column is calculated. This is done using the order func nb function, if you recall. So we treat our columns as independent backtests, and we assign to each backtest $100 of capital. By default, without specifying the size, VBT will use the entire cache, that is size of infinity. Remember that np.inf we were using. So since each signal is executed at a different point of price history, the absolute size is different across all signals, right? The higher the price, then the lesser the lot size or something. But they are using the same amount of cache, which makes them perfectly comparable during the simulation phase. So from the above data frame, we see that there is no column showing where the order was stopped out. Like, did the entry order hit a stop loss or a take profit is still unknown. So in this section, we will see how to go about creating this StopType field. So what we can do is to create our own order records with custom fields, copy the old ones over, and tell the portfolio to use them instead of the default ones. First, we need to create an enumerated field for stop types. So SL levels will come first, and then TP levels come second in an incremental fashion. So to extend the order records, we just need to append new fields and construct a new data type. This is what we do here with a custom order data type. Now we'll see the inner workings of this fix order records function. The function accepts the arguments of our order records, which come from the portfolio simulation results, this one, and then it also accepts our familiar named tuple containers, the signal info and the temp info. So the basic goal of this function is to fix the default order records and add that missing StopType column. So the first step in this process is creating a new empty record array with the new data type, custom order DT. So empty here means that the array isn't initialized yet and it contains junk data. So thus during the initialization, we make sure to override each single element. So the first for loop here copies the existing information from our present order records. The second for loop is used to iterate over the new records and fill the appropriate stop type. So each column in our record corresponds to a signal which we store in this variable called signal. So the order type is filled in our default records by extracting the relevant order type from the signal info NamedTuple container using the signal itself as a key. Then we concatenate the SL and TP row indices of this signal into this new list called bar. And lastly, we check whether the row index of this order is in this list, which means that this order is a stop order. So if the row index of the order is indeed in this list, then we get the matching position in this list and use it as order type, which will correspond to a field in the stop type. So if the row index is not in the list, then we store -1 in the stop type field, and then finally we return the newly created custom order records. So when we call this fix order records function, we now get the stop type column added to our array. So the above raw array output is of our order records is not enough, as vbt.orders doesn't know what to do with the new field. So remember that VBT.orders is used to analyze the records. So now let's create a custom class that subclasses this VBT.orders and overrides that field configuration to also include the information of the new field. So the purpose of this custom orders class basically represents the raw order data in a more analysis friendly fashion. For example, order records have a field size which can be analyzed by querying pf.orders.size. So since we have got new fields, we want to attach them in the same way, and this is done by using this decorator attach underscore fields, which creates the properties around new fields, such as for example pf.orders side underscore by is an automatically created property to filter only the buy side orders. So you see, like, we use that here. So the second decorator, override field configuration, allows us to describe the fields and make them more human readable. For example, title is the name of the field whenever the user prints out pf.orders.records underscore readable. So from the data frame output, we see the usefulness of adding this custom order class, and now we can easily query and filter our order records. So the output, as you can see, is also in human readable format, where the numerical values of different StopType orders are converted into readable strings. So lastly, with the pf.orders.count, we can count the number of orders executed per signal. Next, we'll talk about filtering orderless signals. So we see that many signals did not executed with this order count being 0, right? This is possibly because the entry order never got triggered, as price may not have reached those levels. So in order to filter those signals with empty orders, we can run this np.flat non-zero passing pf.orders count equal to 0 to get the row indexes of those signals that were skipped. So since we have the ID column of the telegram messages, we use these indices to select the orderless signal data points. So it seems we have about 187 orderless signals. So we can remove these orderless signals from our portfolio simulation, which leaves us with only about 45 signals with valid order fields. In this section, we will talk about the analysis and visualization of our backtested signals. So because of this custom order class that we coded earlier here, so we now have like various abilities to analyze our signals and derive statistical information from it. For example, we can count how many times each stop type was triggered. So since we want to combine all trades in each statistics, we need to provide grouping by passing this group by is equal to true when calling this stats function. So from the results, we see that there were 225 signals, that is columns, and the above stats show the distribution of various stop types, where none means that the order was not any type of a stop order. We see that the stop loss was hit like 34 times, while TP3 and TP4 were hit very sparingly at 8 and 4 times respectively. We can also get the stats for positions along with PNL information using this pf.positions.stats, again with group by equal to true, and we see all our typical stats that we would see in a normal portfolio simulation in VectorBT. You can also use the data frame output for the various positions that had to be taken to execute these orders using this pf.trades records readable, and you get this data frame output. So now we'll talk about the difference between orders and positions. So pf.orders is a customized VectorBT representation of the various orders that result from the simulation of our signals data. When we say trades in VectorBT Pro world, they are a bit different from what you would normally call trades in the manual trading world. Right? There are two types of trades, entry trades and exit trades. For example, a position may have several entry orders that increase the position and several exit orders that decrease the position. So the first are called like entry trades and the second are called like exit trades. So pf.trades is the same as pf.exit underscore trades, and for entry trades you can just do pf.entry trades, and that records readable method will give you the output as a data frame. Since we have many types of stop orders, like one stop loss and 4 TP orders and only one entry order for each signal, we have roughly 3 times more exit trades compared to entry trades. That is, here you see like we have 111 exit orders when we print pf.exit orders, and for pf.entry orders we have about 45 entry orders. Moving on to visualization of these trades. So here we are randomly selecting one column, that is one signal, and plotting its exit trades, as we cannot select the entries and exits for all trades and plot them in a single plot, right? Since the only orders that reduce our position are stop orders, so each green or red colored box represents a stop order of this signal. In our case, a green box is a TP order, means that that position closed partially. A red box is an SL order, while the blue box is the blue smaller box is the indication that the market order was executed or initialized at this position. Okay, so here this is like TP1 and TP2 were hit. After that the price reversed and closed out in a loss. So in this section we'll talk about checking the order entry to be within the candle. Let's consider the following scenario, where the Telegram channel gives us signals at an entry price that is too optimistic to be executed at the current time. For example, the signal provider could provide a much higher price for a sell limit order to make the trade appear more profitable than it really is. So instead of manually checking whether the order price is within the expected range, the OHLC range, there is a property called pf.orders price underscore status that does the check for us and returns the status for each order. For example, it returns below low if the requested order price is lower than the low price of the bar where the order happened. We can also use pf.orders.bar underscore high to get the high price of the bar where an order happened, and then we call to underscore readable to make it into a pandas series so that we can put it into a data frame. The same goes for this bar underscore low. So by putting this high, low and price status alongside each other, we can analyze whether the order price is within its candle, and we are passing this title is equal to high and only values equal to true into this readable function, to readable function, so that we only get a pandas series and not a data frame output. So to check for the value counts of the priced underscore status column, we simply can do like dot stats and put group I is equal to true. And likewise, to see the high bars which occurred for each signal, we can run this command pf orders bar underscore high to readable. That just gives us the data frame output. So now we'll talk about merging the order records for seeing various portfolio metrics. So let's say we are interested in various portfolio metrics like Sharpe ratio, etc. Since most of our metrics are producing multiple intermediate time series of the full shape, because we are treating each signal as its own column and thus the simulation is independent, we will have to tile our data by the number of columns. So when we are tiling the data, it's sort of disastrous for our RAM. It increases the memory requirements. So That's why we do this merge order records function. It basically creates a copy of our order records and merges the order records of all columns into one, making it appear as if we did the simulation on just one column. So the string columns like order type, stop type, and side, they are all converted back to the integer data type when doing this merge order records operation. And we also need to change the wrapper for our portfolio object, because it holds the information on our columns which we now want to make one dimension, right? So we had like 232 columns. Now we want to reduce the dimension to 1. That's why we do ndim equal to 1. So VectorBT portfolio object is quite versatile, that when we just print it, we can see the shape of the various array objects inside it, which we can then inspect to decide if any array requires merging by another custom wrapper. So from the output, we see there are no arrays that require any special wrappers. Thus we'll only replace the records and the thus we'll only replace the records using this merged order records and wrap it with our custom merged wrapper. So the previous individual portfolios were each using the starting capital of $100, which was used fully, like 100%. But since we have merged the columns together with this merged order records operation, we now require less starting capital. Thus, we'll determine the starting capital automatically by passing this init underscore cash equal to true. This means the automatic the initial capital is arbitrarily selected, calculated from the max amount of cash we spent during all the simulations. So this is better than taking $100 and multiplying by the number of signals, since then we would have inflated the returns. So you may wonder why the win rate here and other trade metrics are different from the earlier result for each simulation here. So there are two reasons. Portfolio stats uses exit trades. Previously we used positions, that is each stop order is a trade. So after merging, there is no information like which order belongs to which trade. Thus positions are built in like a sequential order. But to verify that the portfolio simulations match between the two different simulations, that is one without doing the merged order records and one doing the merged order records, we can compare the total profit to the previous trade P&L. So here when we print the total profit, we see it is minus 0.57, and it was also the case when we do the P&L.sum with our original portfolio simulation. And we can also plot the entire portfolio simulation using the dot plot show, and we are resampling it into dot daily to make this a little bit more faster and responsive. This is the normal portfolio plot that you are all familiar with. Section, we will see a walkthrough of this custom order simulator, which is basically putting together all the stuff we had seen earlier. So one may first ask, what is the need for a custom simulator? So the main issue with using our from order func is that we need to go over the entire data as many times as there are signals, because the order function is run on each signal or element. A far more time efficient approach would be processing these trades in a sequential order. So this is easily possible because our trades are perfectly sorted. We don't need to process a signal if the previous signal hasn't been processed yet. Also, because the scope of this notebook assumes that the signals are independent, we can simulate them independently and stop each signal simulation once its position has been closed out. And this is all possible only by writing our own custom simulator. But don't get scared, it's not as frightening as it sounds. So to avoid duplicating our signal logic, we will reuse our order func NB function by passing our own limited context object. It will only consist of the fields that are required by our order func NB function, which is this order context. Now let's see this custom simulator function, signal simulator underscore NB. Technically, the custom simulator is just a regular number function that does whatever we want. So what's special about this? It calls the VectorBT's low-level API to place orders and updates the simulation state such as the cache balances and positions. So the general process is we'll first determine the bars where the signals happen and then run a smaller simulation on the first signal. So once the signal position has been closed out, we'll terminate the simulation and then continue with the next signal until we have processed all the signals. So in this section, we basically determine the number of signals, the levels, and the potential orders. The next step is the creation of various temporary arrays. So this signal bars array will hold the bar where each signal happens. This order records array will hold order records. So initially the order records are uninitialized junk data, but we will fill them gradually. Notice how we use our own data type, that is this custom order DT, which we created earlier. And this will fill the order type and stop type fields correctly during the simulation. To be able to distinguish between initialized and uninitialized filled orders, we will create another array holding the number of filled orders for each signal, which is this order counts. For example, if the order records has a maximum of 6 rows and only one record is filled, then the order count will be 1 for this signal. So VectorBT can remove 5 unfulfilled orders later. And order func NB function requires this last position array, which holds the position of each signal. So first we need to determine the bars where the signals happen. So even though we know the timestamps, we need to translate them into absolute indices. So we use a while loop to iterate through the entire number of signals and the total number of bars in our price data. In this if condition, we check if there is a match. If so, we save the bar and continue with the next signal on the next bar. This elif checks if we haven't hit, checks if we are past the signal, and if so, we continue with the next signal on the same bar, which is the plus equal to 1. Lastly, in the else, we check if we haven't hit the signal yet and then continue on to the next bar. So once we know the bars, we can iterate over the signals in a loop and simulate them independently, which is the reason for this for loop. So if there was no match in the previous level, we will skip the simulation. And this is our initial execution state, which holds the most important cash balance, and we see we have an initial starting capital of $100. And now comes the actual simulation in this nested for loop that starts from the signals bar and ends either once we have processed all the bars or once the position has been closed out, which we will see below. So first we again create this named tuple, which holds this current context. This is basically our C in our order func NB function, if you recall earlier when we were talking about order func NB. If the first bar has no data, we simply skip the simulation. So this price area variable holds the OHLC of the current bar. Now we redefine this execution state, and you may wonder why. This is because we need to manually update the valuation price and the value of the column to be able to use complex size types such as target percentages. For example, as in order func NB, we will use the opening price as the valuation price. So VectorBT cannot do this update manually because it doesn't know anything about the other columns. For example, imagine having a grouped simulation with 100 columns sharing the same cache. Using the formula we have here, we wouldn't consider the positions of the other 99 columns. So that is why we have to redefine this execution state. Now let's call our order func nb function, which we had seen in section 3, and that basically returns an order. Now here's the main function in this entire simulation, this process order nb. So its purposes are it executes the order, it updates the execution state, and it also updates the order records and order counts. Notice we pass this signal argument twice, the value twice. It is because one is used for grouping and one is used for column. So columns in our case are signal. When there is no grouping, then group is equal to column. You can also see this in the definition of this function. You see the first is used for grouping and the second is used for column. So if the order was successful, that is, it is now in our order records, we need to manually set the order type and the stop type. So we use this filled order to get the last order of any signal, and we fill the order type of the signal in this filled order variable. We then fill the stop type by going through the various SL and TP levels and checking whether the order bar matches the SL or TP levels. This is that section of the code where it checks if the order bar matches SL or TP levels. So if the order bar hasn't been matched, then it is not a stop order, and we fill the order stop type as -1. If we are not in a position after an entry anymore, we simply terminate the simulation. Lastly, we remember to update the position array, and finally we return a flattened one-dimensional array of our order records. So number requires our arrays in NumPy format, and to avoid preparing them each time, let's create a function that's the signal simulator function that only takes the data and the signal information and does everything else for us. So if you see that we use this build temp info, which clears our signal info NamedTuple context every time for each simulation. So we then call our signal simulator NB function that is written above here to return our custom order records after processing the signals data. So flexible indexing requires that we pass our OHLC columns as 2D arrays. Now that we have our order records, what's left is wrapping them with a portfolio object, for which we require three things. First is the array wrapper with the index and columns, and then the order records and the prices, and of course the initial cache balance and the custom order class. We also specify this initial cache as in the starting capital that we used during the last simulation. So that's it. We can now run our custom simulator function and get the output, the portfolio result. So as each signal is having its own ID, it is represented in a separate column, which we see is this index. The index is basically the IDs of the telegram signal messages, which can be used to retrace back to the source message. So if you recall in this vbt.array wrapper here, in the signal simulator function, we pass this pd.index signal data get id values name equal to id to the columns argument. So this is done to retrieve additional information about the signal using this id column. So the message ID will now be displayed as column names, and you can analyze them using this pfid.stats function. And now you can see individual portfolio stats for each Telegram signal by its ID. To summarize what we have done with this customized signal simulator function, we basically start with the from order function, removed the redundant parts from it, and introduced some optimizations. In the from order func, each signal column required going through the entire data from the start to the end. But in our custom simulator, we skip these parts, which make it much faster. We also create temporary arrays and write our own custom records in place instead of fixing them after the simulation, which is very convenient. The only part that isn't integrated is merging the records, but having the records partitioned by the signal provides more depth and is overall better for the analysis. And now you, the user, can still merge them at any time after the simulations with the functions that we have developed previously. So I hope you enjoyed this tutorial and found it useful. Until next time, see you, take care, bye.